Section 8.10 is called delta connection. Before we begin, it's sort of a backtrack here. He talks about a three-phase load is said to be balanced when each of the impedances of the three phases are equal. Now, we saw that when we looked at the Y connection, but that is something that's fundamental for these relationships, these equations that we're using, the derivation of the equations. So it counts on the three-phase loads, all three of them being equal. And of course, we want to think of those as impedances in general because, you know, it's mostly not just a resistive load. There's usually at least some inductance in these impedances as we look at them. Okay, so now what we've done, we looked at the Y configuration, and now we want to explore the delta configuration. It's better to look at it than talk about it, so let me bring up what that looks like. So what we're looking at here, when we look at the impedances, the Z values here, we're looking at delta connection. And of course, you can immediately see the difference between the delta configuration and the Y configuration. What we see is that the loads are connected end to end, right? And so when we talk about delta in general, you know, we know that symbol delta, and that's what this looks like. They're connected end to end. Out here, the coils or the induced voltages aren't shown, but you know, they would reside out here, and there'd also be one from A to C, but you know, they're not shown here. It's just easier to look at that without those being in place. So this gives us the delta connection. So what we want to do is we want to determine the voltage and current relationships in the delta configuration, delta connection. We'll do that initially with resistive loads just because it's simpler. We will see that the resistors are connected across the line. The resistors are connected across the line. Like if we look at B to C, resistors connected across the line. A to B, okay? B to C, you know, they're all connected across the line. Did I forget one? A to C, I'm sorry. And so, and we also should note that since these are resistive loads, that the current and voltage relationship will be such that the current is in phase with the voltage that causes it. As I look at this first figure here, this 815A, I can think of Kirchhoff's current law, and I can pick a node, and I can say that sum of the currents entering the node equal the sum of the currents exiting the node. I can define, first off, I'm going to do it a little differently than he does. But if I looked at this first one and I wanted to describe, I1. I1 is going to be equal to the sum of the currents entering the node, the sum of the currents exiting the node, okay? 1A is entering, 1, 3 is entering. So I1 is equal to IA plus I3, Kirchhoff's current law. What he has done in our textbook, he has solved this for this I sub A. I sub A is equal to I sub 1 minus I sub 3. And that comes out to be equation 8.5. He does that 2 other times with IB. Again, if I looked at IB here and I picked a particular node, which I will look at that as this node. And I could say the sum of the currents entering the node equal the sum of the currents exiting the node. I'm going to start with I2 is exiting the node. I1 and IB are entering the node. Then I'm going to solve this for IB, and I'm going to get that IB is equal to I2 minus I1. Hope that you can see that. I won't do that the third time. I'll just write down our third equation. So we'll have all of these. Slide this up a bit. And so finally, the third equation is going to say I sub C is equal to I sub 3 minus I sub 2, following the same idea that we did in the earlier two. Okay, so walked you through a couple of examples how we got to the certain point. Now, let's go through sort of discussion like we did with Y connection in terms of voltage relationships. Okay, and like I told you, we won't go through the full mathematical derivation of this, but I wanted to show you this. Okay, so here's our original figure showing the delta configuration. This is a phasor representation of that. And what we see from that is the current and voltage relationships here. And so I can see that I1, okay, I1 is in phase with the voltage EAB. Makes sense, right? Because this voltage is across this. Let me do this. See, this voltage here is across here, right? So it goes to show, or it goes to reason, that this I sub 1 here is going to be in phase with the voltage that caused it, right? And then, you know, the other relationships we can also determine, keeping in mind that each of the voltages are 120 degrees apart. So as I look at this thing, I'm going to take this portion of this, I'm going to turn it around so we can look at it a little easier that way. And I could go through and do that same thing that I did with the Y configuration in terms of the voltages. And now, instead of voltages, I'm referencing currents. And the reason that I'm doing currents instead of voltages again is that I can complete this in the same way, you know, with the law of cosines or law of sines, whichever I want to use. And I can determine, you know, what the equation would be that would describe the line currents in relation to the other currents. Okay, and we'll call the other currents branch currents. And when we look at this, you know, that's, again, here is line current. Why line current? Because it's connected to the line there. That's the only way that we know that that's true. And we're saying that the line current has a relationship to these branch currents. Okay, so you know that's where we're coming from, and that's where we're defining these things. And again, we could go through this same process, and we could determine, you know, what those are using these relationships, and we would come out with the same end result that we had earlier. But we won't do that, and I'll just go ahead and write this for delta. This is going to get us to equation 8.8. and then I'll read at you and see if this makes sense. Okay, so the resultant phasor diagram in figure 815b gives us, through simple trigonometry. Now, when I was in school, I never thought there was anything simple about trigonometry. I don't know about you guys, but that's kind of like saying it's easy as calculus, right? Okay, but anyway, it may not be easy, but we enjoy it, or we wouldn't be in this stuff. But anyway, so I come up with this idea that this line current is going to be equal to 2 times the branch current cosine of 30 degrees. I'm going to do that same thing again, and I know the cosine of 30 degrees is 0.866, which is also equal to square root of 3 divided by 2. And again, the only reason we do that is so we can do this. And I end up with this idea that the line current is equal to, in a delta configuration, the square root of 3 times the branch current. Wow, isn't that cool? That is the corollary of the Y configuration, and this same number, 1.73, that really comes from all of this, and we walk through all that with the Y configuration. And so when I'm looking at line current, I know that the line current is equal to the square root of 3 times the branch current. These are all given in terms of effective values. You know, this final equation. If we need peak values, we can do that, but these are all given to us as effective values. And he says that, you know, it summarizes all of this in table 8A, and I'll bring that up. Why don't I do that now? I'll bring this table 8. No, I'll tell you what, let's work a problem. Let's work a problem. Let's say that we're working 8.5. And let me clean this up a little bit so that we can get all this on one page. Where that circle came from. Okay. And I'll tell you what, let me just do this. I'm going to leave that there. And I'm going to come up with this. Okay. Example 8.5 says we have 3 identical impedances. Okay, I have a separate slide for that. My bad. I have 3 different impedances, and they are connected in delta across a 3-phase 550 volt line. Oh, wow, he's got everything we need here. Here's our voltage, and here's our delta connection, right? 1 to 1 to 1. So they're connected together in delta. And each one of, he says the line current is 10 amps and 550 volts. We've got everything we need. Tell me what the current is in each branch current. Okay. All right. So we can do that, right? We can do that. And that branch current is going to work from this equation. I mean, the line current is going to work from this equation that says the line current is equal to the square root of 3 times the branch current. Okay. Line current, I want to know branch current. That's a Z, not a 2. So I want to solve for I sub Z. So I sub Z is going to be equal to line current divided by square root of 3. Line current is 10 amps divided by square root of 3, and it's going to come out to be approximately 5.77 amps. Okay, so this is 5.77 amps. This is 5.77 amps. Okay, so we were able to determine what those branch currents were in the configuration. And he says, what is the voltage across each impedance? Well, if we look at this impedance is, let me highlight this in a different color. This impedance sees this voltage, which is 550. This impedance sees this voltage, again, which is going to be 550. And this impedance here is going to see 550 volts across it as well. So Z is going to be 550 volts divided by the current, which is 5.77 amps, and that's equal to 95 ohms. Okay, now, again, you know, you look at that and you say, well, how can all this work out? Okay, you know, we did all this earlier, guys. You know, we went through all this with the Y configuration, why these values come out with this. And if you want to take that same process that we did in the earlier, I made 4 different videos for section 8.8. You could go back, or 8.9, and you could go back and instead of putting voltage in there, you can think of this in terms of current and get that same thing, okay? But at the end of the day, what we want to do is recognize the configuration and use this equation to work through this thing. Okay, quick pause. Okay, then he says, let's look at table 8A. And so here we go. In table 8A, we've got the Y connection and we've got the delta connection. What do we want to do? Well, first off, we want to be able to recognize, you know, how these differ in terms of the connection scheme. And I think, you know, I think by now you probably are getting that, right? And, you know, you see that common connection for the Y point. You know, all 3 of the loads have a common connection in a Y configuration. In a delta configuration, it is different in the sense that the loads are all connected. I don't know how you want to say it, tip to tail or whatever, but they're all connected that way. You know, where, you know, they're all connected together. All right, so that makes a delta connection. And then, so what's neat about this, or one of the neat things about this, is this table here that gives us these relationships. So when I'm looking at current, if I want to think about current in a Y connection, it's the same in each element. The current in the delta connection is equal to the line current divided by the square root of 3. Difference with current is that the current in a Y connection is equal to the line current. The current in a delta connection is equal to the line current divided by the square root of 3. The voltage across each element in a Y connection is equal to the line voltage divided by the square root of 3. The voltage across each element in the delta connection is equal to the line voltage. Okay, so here's my suggestion for you. Learn one in terms of the voltage and current relationship. The other one is the opposite for those 2 things. And then I also know that the voltages across the elements are 120 degrees out of phase. The voltages across the elements are 120 degrees out of phase. The currents are 120 degrees out of phase of both. But these 2 things are where the differences are. The current in a Y connection is the line current. The current in a delta connection is the line current divided by the square root of 3. The voltage in a Y connection is equal to the line voltage divided by square root of 3. The voltage in a delta connection is equal to the line voltage. Okay, am I done with that? Yes, I think we are done. We got all that. We finished it. Everything looks good. Going back here, what did I forget? Did I forget anything? I think that gets us covered for 8-10.